Okay, so you have this table. Where's my pen? Oh, you have this table of T in minutes, so 0, 2, 5, 9, 10, and then H in degrees. So it says, as a pot of tea cools, the temperature of the tea is modeled by a differential function H from between times 0 and 10. T is measured in minutes, and H is temperature measured in Celsius. Values of H are selected at the different times shown above. A. Use the data in the table to approximate the rate at which the temperature of the tea is changing at time 3.5. Show the computations that lead to your answer. So how would you do that?
I'm gonna be honest. We just started this stuff, so I'm not gonna be as good at it. But I think is it something with you have to take the derivative?
So for the average rate of change, yeah. So what they're asking for is a rate. So that when you hear the word rate, you should think derivative. Yeah.
Yeah.
So they want H prime of 3.5. But how would you find that using the table?
They want each time. Oh, I would just. That's like you just take the two values like that. 3.5 is between, I think. So it's H of 5 minus H of 2 over 5 minus 2, I think.
H of 5 minus H of 2 over 5 minus 2. Yeah. And this actually comes up in physics too, average rate of change. They'll ask you
really?
like almost literally the same question. Yeah.
That's good.
So you can use it in both places. So what would you plug in there?
For H of 5? 52.
Okay, minus
60.
Divided by
over 3.
What do you get?
Negative 8/3.
Okay, so in degrees, it's like 2.67. Yeah. Degrees C. Yeah. Per minute, because it's a rate.
Yeah.
So the units on top were degrees C, and the units on bottom were minutes. So you got to follow your units. In terms of scoring, it's just you're right or you're wrong. There's no partial credit for part A.
Okay. Sounds good.
Part B says, using correct units, explain the meaning of 1/10 of the integral from 0 to 10 of h of t dt in the context of this problem, and use a trapezoidal sum with the 4 subintervals indicated by the table to estimate the integral. So what does it mean to you to have the integral from 0 to 10 of the function?
The total temperature change?
Yes. Okay. So the total temperature change would be this portion. What does this do to it?
Oh, the average.
Yeah. So it makes it, yeah. So this would have been the total temp change. This takes the average of the total temp change. Yeah.
Okay.
So
I'm not good at the trapezoidal ones.
Okay. Well, yeah. I can make you good at the trapezoidal ones.
Yeah.
So you've got this table, which is helpful because they want you to use 4 subintervals. So it might be helpful if I actually draw the table out so I can show you what I mean. So you've got 0, 2, 5, 9, 10, and then 66, 60, 52, 44, and 43. Okay. So let me use a different color here. So if you look here, let's see, 1, 2, 3, 4. So those are the subintervals that they're talking about. So between 0 and 2, between 2 and 5, between 5 and 9, and between 9 and 10.
So it's just like the lines on the table, right?
Yeah, but that's only because they said 4 subintervals. Like if they had given you a different number, if they had said do 2 subintervals, then you would have had to do like this and this.
Okay.
Yeah, so it depends how many subintervals they want.
Yeah, sounds good.
Okay, cool. So anyway, so there's that. And then how do you find the area of a trapezoid?
1/2 B1 plus B2 times the height.
Yeah, because you're averaging with a trapezoid. This is what a trapezoid looks like. And you have basically a big base and a little base. And
Yeah.
if you were to average it, you'd basically just taking the area of like a square or a rectangle with just
Yeah.
one size base, right? So we're just taking
Yeah.
the average of the big and the little to average it out and then multiplying it by the same height, and then you'd have the area of your shape. So in context of this problem, what that means is these numbers right here are representing your bases.
Yeah.
hmm
And then
and then
so
these are
then the
your
other one is just
heights.
the height. Yeah.
Yeah, so this is B or B, and this is H. So H being
So it's 1/2. You just do 66 plus 60 divide times 2 for like the first
66
one.
plus 60 divided by 2 is the average of those bases, and then times the height. So what is the height between the interval here that we drew?
2.
Yeah. Okay.
So just 66 plus 60.
Well, let's show our work though, because
Yeah.
what's the next one?
Big. 1/2 60 plus 52 times 3. Right? Yeah.
Mm-hmm. What else?
And then 52 plus 44 times 4 divided by 2. And then 54 plus 63 divided by 2. That's it. It's the height's only 1. I'm going to go get my calculator real quick.
So all of this would represent the integral. So this is representing that total, but we have to remember to multiply by the 1/10 to get the average.
Yeah. Okay. Sorry. Four, 3, 5. It means 5.3. Does that make sense? Hold on.
I wonder if they forgot to divide by 10 because their answer is 52.95, which would round to 53. So they're 10 higher than you. Did they forget to divide by 10? Or did you divide twice by 10?
No, I divided twice by 10.
Okay.
Let me just do this again and see
what happened. This is like totally.
Yeah, I got 53. I got 52.95.
Okay.
Is that correct?
Yep, that is correct. And let's see, what would, ironically, they were very specific about making sure you use the correct units. Then they wrote their answer with no units at all. What would the units be?
I think it's just degrees.
Yeah, the average temperature. So that would be degrees C. So in terms of scoring, you would get 1 point for the explanation where you talked about how that represented the average temperature, 1 point for showing your work for the trapezoidal sum, and 1 point for getting the correct answer.
So I have to explain that, like, I should just do what we did up there, like say this is the total temperature, and then if you divide it by 10, that makes it the average temperature.
Yeah, I mean they just wrote a sentence. They said that that entire thing represented the average temperature of the tea in degrees Celsius over the 10-minute time period. Like they wrote a sentence. But yeah,
Okay,
I think honestly if you just wrote what we wrote, it would work too. But if you want to be safe, then write it in sentence form. Yeah.
sounds good.
But yeah, 1 point for the sentence, 1 point for the work, and 1 point for the answer.
Okay.
Okay, so then part C says to evaluate the integral from 0 to 10 of h prime of t dt using correct units, explain the meaning of the expression in the context of this problem.
Oh, that seems like it's just h and t evaluated from 10 to 0.
Wouldn't it be because the integral of a derivative just brings it back to where it was? So
Yeah,
what would you say it in words though? Because they want you to talk about the meaning.
the meaning of the expression. So the integral of the total, is this total change in degrees? Since
So
it's,
so it's basically the total change in degrees
okay,
from 0 to 10. So let's figure that out actually. So um, what you were saying is when you took the integral, if you were to show your work, you taking the integral of h prime of t just gets you h of t, right? And then it has to be evaluated between 0 and 10.
yeah,
So you plug in h of 10 and you plug in h of 0, right? F of b minus f of a.
yeah,
So they do want to
okay.
see that work. And then look at the table, and what do you get? H of 10. What's h of 10?
43
Okay.
minus 66, you put negative 23.
Okay. And so what does that answer represent?
Like over the 10-minute period, it cooled a total of 23 degrees.
That would be a really great explanation. Yeah, they wrote the temperature of the tea drops 23 degrees Celsius from the time t is 0 to the time t of 10 minutes. So I think that your explanation would be perfectly acceptable. So the tea
Awesome.
dropped 23 degrees C over 10 minutes, something like that. So you would
Yeah,
get 1 point for getting, like doing the work here and getting the negative 23 degrees C, and 1 point for interpreting the answer and explaining what that number meant.
awesome. Pretty nice.
Okay, part D says at time t is 0, biscuits with temperature of 100 degrees C were removed from the oven. The temperature of the biscuits at time t is modeled by a differentiable function b, for which it is known that b prime of t, so they gave us b prime of t is equal to negative 13.84 e to the negative 0.173 t. Using the given models at time t is 10, how much cooler are the biscuits than the tea? So they really are checking if you're paying attention to what they're asking.
Yeah. So do you just how much cooler? So can't you see like how much it cooled overall because we know the initial thing. So if we just did from zero, the integral from 0 to 10,
Okay.
and then so that would be like we'll call it b of 10 minus b of 0, right? Or wait, so is this do you know if this is a calculator problem? Because I like think on the AP exam this is just like you set it up and then they would like just have you.
Let me see if it says calculators or not. It might say it at the top. It does not say whether it's calculator or not, but the numbers they're getting are decimal form, which makes me believe that they're expecting you to use a calculator.
Yeah. 173. You need to add the initial. You need to add the initial to it. It's h of 0 plus the integral from 0 to 10, right?
Okay, and what's the initial?
100.
Okay, so you've got 100 plus.
And then
So
I calculated that value. The the integral, and it's negative 65.82.
But 100 minus that, right?
Is 100 minus that. That's what.
Or plus the
So
negative number. Yeah, I should say.
we'll just say like 34 or.
Yeah, they got. We'll just call it 34.18. They went like
Okay.
so many decimal places out. But anyway,
Yeah.
so that's not the answer. Why not?
Because you have to find out how much cooler the biscuits are than the tea.
So you've got to look at what the temperature was of the tea at 10 and then subtract the answer you got of the B at 10.
Yeah. That's just like 8.82.
And
okay,
what are
I'm
your
gonna go get a new
units?
pen.
Okay.
8.82 degrees Celsius.
Okay, go ahead. Get your pen.
All right.
Okay, so for this problem, in terms of scoring, they knew that most people would know this part, and they knew a lot of people would forget this part. So that is actually separate points. So knowing that you had to use the integral is worth 1 point. Remembering that you needed to add the 100 to it is worth 1 point.
Yeah, I
And
just
then,
remember that. Can you explain why you have to add it? Like, why do you have to do the initial too?
yeah, well, you started at 100 degrees and then you started to cool off. So you didn't start at 0, right?
Right. So you just have to say that, and then you have to do your initial thing and then show what changed about it. Basically.
Yeah, exactly. Yeah. So the function is how much it changed, grew or shrunk or whatever, but you've got a starting point. It's like when you're born, you're born usually like 20 inches long, and you can talk about like how much you grew in the year that you're alive, but you wouldn't want to forget that you started somewhere. You didn't start at 0, right?
Yeah. All right. I want to do that. There's another one for 2011, number 5.
Okay.
And that one has like is it called related
rates or something like that?
Yeah, I think it's related rates. I can't see your iPad.
Yeah, it went away. Let me.
Okay, that's okay.
Reshare.
Yeah, I'm really bad at related rates.
Okay.
Hard little thing.
There we go. Okay. So number 5. Number 5. Okay. At the beginning of 2010, a landfill contained 1,400 tons of solid waste. This is fun. Why is that happening?
Wait.
Is that not the one?
So, no, it's 2011, number 5.
That's what I'm doing.
Oh, 2011. Maybe there's 2 sets then. Oh, okay. It's Form B. It's Form B.
Form B. Do I have to just scroll further, or is it?
Oh, no, you just have to look up. I'll just look up Form B and send it to you real quick.
Wondering if I need to restart my iPad again. It's weird.
Yeah, here it is.
Not what I meant to do.
Do you know how to do like SAT math? Like, is that something you tutor?
Yeah.
Okay. I'll probably end up getting help on that for a bit too.
Why can't I figure out how to shut my own iPad down? Don't you just hold the button? You hold the home button and the side button, right?
I think so. I don't have an iPad.
Usually it just shuts down. It's up and all it's doing is taking screenshots. I don't need screenshots.
Is it just? I think it's just. Is it just power button? I don't know.
I don't know. Let me open the link you sent me. Okay. Let's see. Okay. And you said number 5 from Form B. Okay. 1, 2, 3, 4, 5. Okay. So it's the one with the table.
Yeah, it's about his unicycle.
Okay. So force quit that app and see if we can go back into it. Okay, Ben rides a unicycle back and forth along a straight east-west track. The twice differentiable function B models Ben's position on the track measured in meters from the western end of the track, north, south, east, west. Okay. At time t measured in seconds from the start of the ride, the table above gives the values of B of t and Ben's velocity V of t measured in meters per second at selected times t. Okay, cool.
Okay. It seems kind of similar to the last one. A.
Yeah. A, use the data of the table to approximate Ben's acceleration at time t is 5 seconds, indicate units of measure.
So would you just do V prime 10 minus V prime 0? Or no, just V of 10 minus V of 0 over 10, right?
10 minus 0, yeah. It's the same. Yeah, B prime or just V. V is B prime, so I don't think you'd get marked down for that.
Yeah.
And then just tell me what you get.
V of 10. Just 0.3 over 10, like 0.03. Does that make sense?
Yeah. What are your units?
Meters per second squared.
That's correct.
Awesome.
So part B, using correct units, interpret the meaning of the integral in the context of this problem and approximate it using the left Riemann sum with the subintervals indicated by the data in the table.
Interpret the meaning of it. Okay.
How do you do it?
Like, what does it mean, or how do I do it? Oh, left Riemann sum.
What does it mean first?
Oh, I think it is just describing the total change in meters.
Total distance in meters that Ben rides over the 60-second interval. Yeah.
Total distance ridden over 60-second interval. And then left Riemann sum, is that the one where it's like it says with the subintervals indicated by the data?
Mm-hmm.
So is that where you start at the left? Like you start with the first value instead of starting with the second value? I don't know, that's not exactly how it is, but that's how I used to think about it.
Yeah, that's a way to think about it. Yeah. Oh, if my iPad would cooperate, I would draw you a visual. But yes,
Yeah.
So the left Riemann sum means that like if you're drawing rectangles, the left side of the rectangle hits the function and the right side just draws the rest of the rectangle. Versus the right Riemann sum, the right side of the rectangle is hitting the function and the left side just goes out and drawing the rectangle. Yeah, and then there you've got the, what do they call it? The mid sum or mid Riemann sum or something? The one in the middle where you do like the middle of the interval. So there's that
that's
too.
like the average. It's divided by 2.
Yeah.
Adam. Okay.
Yeah.
So it's just 2 times 10.
Okay.
Plus 2.3 times 30 plus 2.5 times 20.
What do you get?
I've not done it yet. Hold on one sec. 2.5 times 20. I definitely know how to do 2.3 times.
No.
I get 139.
What are your units?
Meters.
Very good. So you would get 1 point for understanding the meaning of that integral and 1 point for the approximation. So here's just really briefly, this is what I wanted to sketch for you. So let's say you have like this random function. So a left Riemann sum is doing this. You're hitting the left side of the rectangle and drawing the rectangle. So this is left.
Mm. Okay.
Sum. And then the right Riemann sum's opposite, maybe I shouldn't draw it at the same place. That might be a little confusing. But the right side of the rectangle hits the function.
So if it's I'm going to try and remember this. If it's a concave down function, or is it about concavity, or if it's an increasing or decreasing? If it's an increasing
Of when
function,
to
I
use
remember.
it?
No, because you have to say, is this an overestimate or underestimate sometimes? I remember that.
Yes. So visually, you can see this right now is if I use that red rectangle, you see how there's a lot of area under the curve that I didn't hit? Like
I do.
I
Yeah.
didn't account for this. So that's an underestimation. Whereas if I use the pink rectangle, I overestimated. Look at all that area that's actually not under the curve that I'm
Yeah.
accounting for.
And then if it was the other way, if it was decreasing, it would be the opposite, right?
Yeah, I suppose it sounds like you're trying to memorize it. And my point is, you can
No,
always
I
draw it.
understand it. Yeah.
Yeah, my
No.
point is you can always
Okay.
draw it because look, here is the mid Riemann sum, where the midpoint of that rectangle is there.
Yeah.
And you see how then that sort of accounts for the fact that you're overestimating and underestimating a little bit, like it averages it out. So yeah, in that part of my graph, it's concave down, so maybe you could memorize it. But what if I moved over to this part of my graph? Like, is your answer the same of underestimating and overestimating? Like, so one graph could be both concave up and concave down, depending on what interval you're looking at.
Yeah.
So you might as well just, at least visually in your brain, sketch it and think, am I under the curve or over the curve? Am I overestimating or underestimating? It's fast enough to just sort of draw it and figure it out. Because you don't want to only memorize it because then if you're wrong, you're just wrong. Whereas if you can just look at it, then you can figure it out,
Yeah. Okay.
Okay, so part C says between time is 40 and 60, must there be a time t when Ben's velocity is 2 meters per second? Justify your answer.
Isn't that just you? I think this is low hanging fruit. Don't you just say yes according to the intermediate value theorem? There's a value.
I think they'd want you to show it though, like prove it.
Oh, okay. I don't know how to do that.
It's the same work basically that you did in part A, but you're just using the B function instead of the V function. So
okay. Wait, do I use the B function or do I still use? It's asking about the velocity for 40 to 60.
Yes, but when you're doing the rate of change equation, it's calculating the rate of a function. So if you use the B, you're calculating the rate of B, which is then V.
Okay. So between 40 and 60. So that thing between the values 9 and 49, is there a time where it's 2? Like, if it's 2 meters per second.
Yeah, and you can prove to yourself the units too, because if you're doing this is part C. So if you're doing B of 60 minus B of 40 divided by, remember it's rate of change, so divided by 60 minus 40. So like you said, 49 and 9, right? But what are the units of 49 and 9?
Second. Meters.
And then what are the units of 60 and 40?
Seconds.
Okay, so your answer comes out to meters per second, which is a velocity.
Oh, okay.
So you can check your work to make sure your units line up with what you're looking for. So what do you get there?
2 exactly?
Yeah, you do get 2 meters per second exactly. So you would say by the mean value.
Okay, so this is mean value theorem?
Yeah. By the mean value theorem,
there must be a time t in the interval.
Yeah, there is a time between 40 and 60 that the velocity is 2.
Cool.
So you get 1 point for showing your work there with the math, and then 1 point for writing the sentence explaining it.
Okay.
Yeah. Okay.
Great.
D. A light is directly above the western end of the track Ben rides so that at time t, the distance L of t between Ben and the light satisfies this equation. Okay, that looks complicated, but it's just Pythagorean theorem.
Oh.
It's a triangle.
Oh,
It's
yeah,
a
yeah.
squared plus b squared equals c squared. At what rate is the distance between Ben and the light changing, so the hypotenuse of the triangle, at time t is 40?
Oh, your iPad went away.
Yeah,
Yeah.
that's all right.
All right. Well, while you set that up, I'm going to start.
How would you do this?
I know you have. I think you have to plug. You have to plug in. First, I would, if it's asking the rate at which the distance is changing at t equals 40, it's asking how is the hypotenuse changing, or like this line, and then so you have to find the change for the other two. Right?
Well, when you are saying the word rate of change, what does your brain think of when you hear the word rate?
Slope derivative.
Uh-huh. So they gave you an equation and you need to take the derivative. That's like your first step whenever you hear rate.
So I would find L prime of t.
Yes. Yeah. So take the derivative in reference to.
Do I have to isolate L first, or?
No, L of t is one thing. It's just L of t squared. It's like a function squared.
So I just go L prime of t squared.
How would you take the derivative of something squared?
So it's just 2 L prime of t?
Okay. So it's 2 L of t, because you take the 2 out, right?
2 L
and then it's a chain rule. Yeah. 2 L of t times L prime of t. It's the chain rule.
2 L of t times L prime of t. Right. And then do you have to derive both sides? So then,
yes. And so what's the derivative of 12 squared?
0.
Okay. And what's the derivative of b of t?
It's 2 b of t, b prime of t.
Exactly.
Equals 2 times b of t. And b prime of t is just the velocity.
That's correct.
Right? So it's 2 times b t times v of t.
And at this point, you would probably want to isolate L prime of t, because that's what you need.
You can cancel out these 2's. So it's L prime of t equals b of t times v of t over L of t, evaluated at t equals 40.
Yeah, so now you would just plug in, like you'd say, I want L prime of 40, which means I want B of 40, V of 40.
This wasn't that hard.
No, but it was knowing what they meant by taking a rate. When you hear the word rate, you should think derivative.
All right, so B of t at 40, so it's 9 times 2.5. And to find L of t, do I just plug in 40 to that equation and solve for L of t?
Yeah.
Okay. B of 40 says 12 squared, 144 plus 81. And then the square root of that. So it's almost there. 9. 1.5.
Yeah, what are your units?
The rate at which distance meters per second.
Yeah, so they wrote 3/2, but same thing. So
Okay.
1.5 meters per second. Okay, so I have a little note for you. So if you see the word rate, you should take a derivative if they've given you a function. But if they haven't given you a function, they gave you a table, if you hear the word rate, then the only thing you can do is use the average rate of change equation.
Yeah,
Where you
and
do
they'll
like f
always
of b over
say
f of a.
approximate, right?
Yeah,
Yeah.
And so for part D, it was 3 points. They would give you 1 point for doing like this work, like getting the derivative. You
Yeah.
would get 1 point for knowing this portion right here, where you said, oh, b prime of t is v of t. So that's 1
Okay.
point for knowing to do that. And then your final point is actually getting the answers. This one right here.
Super cool.
Oh, and then it looks like in terms of units, they just like overall looked at your page, and if you used units in all the portions, you would get 1 point, and if you didn't do the right units, you would not get a point. So units do matter.
Yeah.
They just like put it as a separate score and not like in each part.
Yeah.
Yeah.
All right. Thank you.
Uh-huh. Okay. What else? Which one do you want to do now?
Did I send you 2016 with a table to water?
I mean, either way, you can just send it to me anyway through the link.
That's true.
Because I don't remember the other one that you sent me. I don't remember it having the problem statements, but these are nice because I do have them.
I guess I don't even need to.
Yeah, you don't need to anymore if it's always going to be these problems.
Yeah. All right. And it is the first one. There you go.
Okay, let's see. Number 1. Okay. Okay. Water is pumped into a tank at a rate modeled with this equation. So water into the tank, 2000 e to the negative t squared over 20 liters per hour between the interval of 0 to 8. T is measured in hours. Water is removed from the tank at a rate. Ooh, interesting.
Yeah.
Cool. This is reminding me of my thermodynamics class in college. Okay. Rate. Oh, but they don't give you that function. Okay, let's see.
No, they do not. They give you a table for it though.
Oh, okay, table.
So it's the same thing.
Yeah.
Not to make a hasty generalization.
Well, this is good. See, that's my point that I was making about like they're giving you both a function and a table. So they want to know that like you know the meanings behind and how to use both things.
Yeah, I think I'm getting it. So we're gonna go 950 minus 10,000.
Oh, they do give you 1 point in time though. They do say that at time t is 0. There are.
So that's for. Okay, yeah.
What is it for? You tell me.
It's like the same thing we're talking about. It's the initial, like it's the initial.
But notice that it's the amount of water that's physically in the tank. The table that they're giving you is the function for the rate at which the water is being removed, and the function they gave you is for the water being put in. The 50,000 is at an instant in time of essentially W minus R.
Oh, okay,
right?
That makes sense. Yeah. Not okay.
W is water putting into the tank. R is water going away from the tank. And at one moment in time, they take a snapshot and they say that delta there is exactly 50,000.
Okay.
Yeah. Okay, A, estimate R prime of 2.
950 minus 1,190 over 2.
Yeah. Show the work and use units is all it says. So what do you get?
Negative 120 meters per second.
Try again for your units. What are your units?
Meters per second squared.
Try again. Read the problem statement.
Liters per hour.
Yes. Try again, closer. Liters per hour squared. Yeah. So getting the 120 is 1 point and getting the proper units is another.
Okay.
So it's worth it to take a beat and just reread the problem, make sure you know what units you're working with. Yeah.
Right.
Okay, part B, use the left Riemann sum with the 4 intervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Is this an overestimate or underestimate of the total amount of water removed? Give a reason for your answer.
Okay. Let's get to it. For removed from the tank during 8 hours. Okay. So that's 13. I'm just going to go straight to my calculator, actually. 40. Um, 8,050
units.
Liters.
That's correct. Okay. And is it under or overestimate and why?
An overestimate.
Why?
I think it's an overestimate because it's a decreasing function since it's bottling a rate of like taking it out.
That's correct. So we had mentioned earlier, you're asking how do you know? And I think we were using the words concavity, but I think it's more so not necessarily concavity, but decreasing or increasing, I guess.
Right.
You don't have this function like I was saying, oh, just draw it. Well, you don't, I guess you could sketch it, but you don't want to take the time to do that. But you can see that the numbers are decreasing because the water's leaving. So because you can visually see the numbers going down, you can think, okay, it's decreasing. So even if you were to just be like, all right, it's decreasing and I am doing, what did they say for me to do? Which one did we do? The right or the left? The left.
Left.
I feel like that would be an overestimate. Oh yeah, that's the answer. Okay.
Yeah, that's what I said.
Yeah, so there's your like rectangle there. If you took the area of the rectangle, you'd be overestimating by this much.
Okay.
Yeah. So you would say overestimate. Honestly, that's how, if I were taking the test, I'd like draw that and show it. Overestimate since it's a decreasing function. And so in terms of scoring, they want to make sure you did the left Riemann sum, the work. You got the right answer with the units.
I have a question.
Yes.
Is it decreasing because it's modeling a rate at which water is getting taken out, or is it decreasing because the values in the table decrease?
No, it's literally the values in the table. Because we only were looking at R.
Yeah. That's what I thought. Like the initial, like the first liters per hour versus the last one.
Yeah, the liters per hour, not that the water's leaving the tank, because the function of the amount of water in the tank is not given to us. We're given the function of water being put in and the function of water leaving, but we aren't actually ever given the function of just the water over time. So we don't know we don't know which one's outpacing which. Right? We don't know if water is going in faster or water is being removed faster, and therefore we don't know if the tank is filling up or leaving. We don't know.
Okay.
But we do know that R in particular, that function itself is increasing. So it's removing water from the tank at a slower and slower rate. Why, we don't know.
Yeah.
But yeah.
Okay.
C.
Yeah. Find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Removed from the tank to find an estimate of the total amount of water in the tank. Do you not just do what we like? The T is 0 is 50,000.
Okay, so you start at 50,000, and how does the water in the tank change?
You have to like model the increase minus the decrease.
So it increases by what? By which one?
WT plus WT minus RT.
Yeah, but it would be the integral from 0 to 8.
Yeah.
And then we already did the math for part.
Yeah, and you could do those separately, right? Yeah.
That would be like your total function. Yeah.
Okay.
Because this is the start, this is the in, and this is the out.
Super. Okay. Let me calculate that then. That's great that I do that. Did not lose that much. I got 49,786
Units.
liters. You have to go where? Okay, sorry, I was talking to my mom.
That's okay. 1 point for the setup and 1 point for the answer.
Okay. Then this is the doozy.
For 0 to 8, is there a time t when the rate at which water is pumped into the tank is the same as the rate at which water is removed from the tank? Explain why or why not.
Do you set the two equal to each other?
Yeah. In my mind, I was thinking like in minus out equals 0, right? So like in minus out equals 0. But then you're right, because if you add out to both sides, so yeah, they're the same. So yeah, but one is a table and one is a function. So what do you do?
I know this has something to do with the intermediate value theorem.
Let's check the endpoints. Okay, so the endpoints of the function, and let's see if it changes. If like the delta between in and out is less than or greater than 0 on one side and on the other, because then that would show that it passes the 0 point.
Yeah.
So, for example, what's W of 0 minus R of 0?
Negative 1,340.
Negative 1,000. How'd you get that?
Well, isn't W0 just 0? Or no, it's 2,000. Sorry. It's 660.
Okay, so that is greater than 0. What is W of 8?
That I will have to find out. 2,000. So much extra stuff for this function. There's no way that can be true. For wait.
We just need to know if the difference between it going in versus out is more than 0 or less than 0. We don't actually need like a.
I'm pretty sure for this one it's also more than 0. Because W8. Is that incorrect?
It says it's less.
Oh.
So let's see. R of 8 is given. That's 700. And then W of 8, wouldn't you just plug it in?
Yeah, that's what I did.
2000. So 2000 e to the negative. Oh, okay. Is the t negative? I don't think so. Negative. So negative 8. Let's see what happens. Over 20. 81.5.
Okay, I got that time.
Okay.
Yeah, I didn't do the negative at first.
Oh, gotcha.
Negative 8 squared beds.
So we checked the endpoint. So what we're just saying is it went like if here's your 0 mark, we had the difference between water coming in and coming out started above
okay, so there is
0.
a time they have to be. Yeah.
Yeah, and it went below 0. So there's some point in time where it actually does hit 0. So you would say that by the intermediate value theorem, there must be at least one time where, and you could say either way, W equals R or W minus R equals 0.
Okay.
I guess to be accurate, I would put of t, like the function. W of t minus R of t equals 0. And yeah, and you can say it your way too. You could say or, where water coming in is equal to water coming out.
Cool.
Or you could put it in words. So you could literally say, like this means water going into the tank is at the same rate as it is leaving at some specific time within this interval. For scoring on that one, they want to know that you're looking at the delta here. So yeah, you do have to look at the subtraction because we never in our math were able to get, we didn't guess and check to find the exact point where they equaled each other. We had to just look at the delta and see if it was less than or greater than 0 and prove that because it's past the 0 mark, that it must at some point be equal to each other.
What if it stayed? So if it's greater than 0 at W0 minus R0 and then greater than 0 at W of 8 minus R of 8, does that mean there is not a value since that?
Yeah, you would show your work. You'd show your work and you'd say, well, at this point of the interval it's there, and at this point of the interval it's there. So,
so if it's less than 0, it has to be 0 at some point.
Yeah, if it goes from above 0 to below 0, it must hit 0 at some point, right?
Okay.
Yeah.
Yeah, that makes sense to me.
Yeah, okay. But I would truly triple check that because my guess is they're setting you up so that it is. That the answer is yes.
Okay. Yeah.
So if
usually it's
yes,
right?
Because they really want to know if you understand what the intermediate value theorem is, and like on the last problem, they want to know that you know, what was it? Mean value theorem.
And you can just recognize it.
Yeah, they're trying to see if you remember to use them and to name them,
right?
Basically.
Okay.
Yeah.